Hello, my name is Oier Mees and welcome to my talk on adversarial skill networks, unsupervised robot skill learning from video. This is joint work with Markus Merklinger, Gabriel Kalweit and Wolfram Burgard. Intelligent beings have the ability to transfer and reuse skills without supervision to solve a new task. In this example, you can see how the orangutan observes another orangutan sawing a tree branch and is able to imitate it. This requires a general understanding of learned skills and to transfer skills to a new task domain. Ideally, robots should also have a similar ability to imitate a visual demonstration by reusing skills. We focus on imitation learning from video data as it provides several advantages. First, recording a video demonstration is a very easy way to specify a task. It can help reduce human teaching effort to robots by avoiding expensive kinesthetic demonstrations or teleoperation of robots. Second, it provides a very rich reward signal to know how good you are doing. And third, it is widely used in nature to reduce expensive exploration, as you can see in this example, where the dogs observe and imitate a toddler's crawling. Let's talk about how we define tasks. There is a tendency to think that the behaviors we want for our agents are a set of discrete tasks like pick up an object, open a door, etc. However, it is difficult to draw a boundary of where does a task begin and end, as it is made up of smaller subtasks or skills. This is why we prefer to talk about tasks and skills as living on a continuum. In this example, you can see the three tasks represented in a continuous skill embedding space. As you can see, the first block stacking task, represented with this big circle over here, is composed of some skills that could be shared with this other same colored block stacking task. This task, on the other hand, could potentially share some skills with this task where same colored blocks are pushed together. Thus, having discovered and learned skills of one of those tasks should help transferring this knowledge to solve a novel task. Intuitively, if the agent has learned a set of skills pertaining to two block stacking and same color block pushing, it should be able to reuse its knowledge to master same colored block stacking. So how can we teach such tasks to an agent? One of the main paradigms currently used to learn flexible behaviors for autonomous agents is reinforcement learning, which has achieved impressive results. However, current agents typically learn solutions from scratch for every task and often rely on manual per-task engineering of reward functions. Furthermore, the obtained policies and representations tend to be task-specific and generally do not transfer well to new tasks. Not only is this inefficient, but also limits the versatility and adaptivity of the systems that can be built. Ideally, we would like to have an agent that can learn tasks without reward engineering and can reuse previously seen skills to solve new tasks from a single video demonstration. The advantage of such a system for robotics would be that it reduces a lot of the engineering effort, as an agent could continuously watch unlabeled videos and try to discover and extract relevant skills from them. Basically, instead of expensive manual labeling of data, we would like a robot to uncover and disentangle what matters of the world on their own via self-supervised signals. As a step in this direction, we propose a novel approach, which we name adversarial skill networks, that aims to learn a task-agnostic skill embedding space from unlabeled multi-view videos. The main idea is to try to discover and extract skills from unlabeled videos that depict some unknown tasks by reasoning over the temporal coherence of the videos and represent them in a task or domain-agnostic fashion on a latent skill embedding space. The distances in the skill embedding space can then be used as a reward signal to guide an RL agent to solve novel tasks from a single video demonstration by reusing previously seen skills. So how does this work? First of all, we define a skill as the embedding of two frames separated by a variable stride. We combine a metric learning loss, which utilizes temporal video coherence, to learn a state representation, together with an entropy regularized adversarial skill transfer loss. The adversarial skill transfer loss enhances reusability of learned skill embeddings over multiple task domains. We're going to explain these 2 points now in turn. In order to capture the temporal task information, we utilize a multi-view metric learning loss that attracts different viewpoints at the same time step to the same point in embedding space, and repulses temporal neighbors, which are often visually similar but functionally different, similar to time-contrastive networks. The advantage of this is that the encoder network discovers attributes that do not change across viewpoint, but do change across time, such as object interactions, while ignoring nuisance variables such as background, motion blur, and illumination changes. To transfer similar skills without any label information to unseen tasks, one needs to learn generalized skills that should neither be task nor domain specific. Since a true class distribution over skills is not known, this problem can naturally be considered as a soft probabilistic cluster assignment task. The discriminator network, which is used only during training, takes 2 concatenated embedded frames that define an unlabeled skill as input and outputs the probability of the skill or being originated from a concrete task. Without label information, we make use of information theoretic measures on the predicted class distribution to group the unlabeled skills into well-separated categories in the skill embedding space. The interplay between the encoder and the discriminator networks works as following. The discriminator minimizes the entropy given an unlabeled skill embedding to be certain about which task the skill originated from. The encoder, on the other hand, besides learning the temporal coherence, tries to maximize the entropy to learn a domain-agnostic skill embedding. Thus, it wants to be unsure about which task a skill could have originated from. Finally, we use an additional regularizer to enhance the equal usage of all task classes, corresponding to maximizing a uniform marginal distribution. To evaluate our approach, we recorded multi-view block tasks datasets in simulation and in the real world. As our method does not require any sort of labels or state information, recording such a dataset in the real world boils down to synchronizing multiple webcams connected to a laptop. We measure the performance of our models based on the alignment loss of viewpairs, following time-contrastive networks. We take advantage of the fact that frames in both videos are synchronized with each other to get alignment labels for free. So basically, we try to sequentially align 2 viewpairs by finding the nearest neighbor in the embedding space, normalizing the distances by the demonstration length. However, instead of evaluating the alignment loss on the same task as the embedding was trained on, we measure how well viewpairs of novel, unseen tasks are aligned. We found that our model yields better results on this than TCN and multi-frame TCN on this challenging evaluation. Next, we analyze how good our skill embedding space can estimate the temporal coherence of an unseen task. Here you can see a TSNE plot of an unseen color stacking video for models trained on block stacking and color pushing, and where the color bar indicates temporal task progress. Our model maintains the temporal coherence of the task better than the baselines. Lastly, we integrate the learned metric within an RL agent to imitate an unseen task given a single video demonstration. In this example, we train the embedding on the tasks of 2 block stacking and block color pushing, and then try to learn a continuous control policy for the color stacking task. The agent receives a dense continuous reward at every time step by computing the distance in skill embedding space from the agent's view with respect to the corresponding time synchronized frame from the video demonstration. To conclude, we presented a novel approach that leverages information from multiple label-free demonstrations in order to yield a meaningful embedding for unseen tasks. The learned and task-agnostic skill embedding space enables agents to solve novel tasks that require the interpolation of skills. Our approach has the potential to reduce the engineering effort to teach tasks to robots by leveraging unsupervised learning from video. This way, a robot could continuously watch unlabeled videos and try to incrementally discover and learn disentangled skills in a way that it could reuse them to master new tasks more efficiently. For more information on the approach, please visit our project website. Thank you for your attention.